Hello and welcome to our video for Math200 Statistics online at Cañada College. My name is Lapuz and we are covering Section 10.2. Alright, let's get started. The section or the chapters start with a review and a preview, so let's take a quick look at that. Our review is going back to Chapter 9. We presented methods for making inferences from two samples. 9.4 in particular focused on dependent samples, and we called them paired values. Now we took a look at how to do a hypothesis test and make confidence intervals for those paired values. Now in this chapter we're going to look at paired values again, but they're going to be different from the paired values in 9.4. The paired values that we're going to be looking at is checking to see if there is a correlation or an association between two quantitative variables. We're going to focus on a linear correlation, and we're going to try to see if there is a correlation between the two variables, and we're also going to try to find an equation if there is in fact a correlation. We should find the equation of a line that best fit the data. So here's our correlation section 10.2. The idea here is we're going to work on linear correlation coefficient. So we're going to introduce a new variable, a value, a statistic that we're going to find from a paired data set. This number coefficient, this linear correlation coefficient, value R, gives us the measurement of how strong the sample data fit a straight line pattern. So we're going to look at this data as they call it a bivariate data, and we're going to be using the TI-83 to find our correlation coefficient. So after our introduction to the correlation coefficient, we're going to perform a hypothesis test to see if there is in fact correlation. The basics of correlation. Correlation exists between two variables when the values of one are somehow associated with the values of another. Now, in some way, that way may not be defined, but we are just looking for association. That's the important part. A linear correlation talks about the relationship between the two variables as being linear, and what that means is that if you were to plot the points of the paired data on an XY plane, then the pattern of that can be approximated by a straight line. So as we explore the data, it'll be important for us to begin by constructing a scatter plot. That is basically a plot of the set of data that we have. Here are some examples of some scatter plots. We have a positive correlation. Our line that we would be looking at would be going up from left to right, so that has a positive slope. Part B, or B example over here, our line is going down, so we would say that has a negative slope. Now, how tight these points are associated with that line tells us the actual value of the correlation coefficient. And it turns out that if the value of the correlation coefficient is closer to 1 or -1, then we have a stronger correlation. If it's a little bit farther away from -1 or +1, then we have a not so strong correlation. Although 0.85 is fairly strong, relatively speaking. Here are a couple of examples where the correlation is weak, or we can actually say that there is no correlation. In this particular example, we can't draw any line that would give us a good correlation that would be descriptive of this data set. So here the correlation is 0. This is another example where the correlation is close to 0, but if you look at it, we can't define or we can't find a line that would best fit this data. But the data looks like it follows a different type of curve. And so when you see something like that, you can assume that there might be some non-linear correlation going on. But this R measurement still comes from a linear correlation. So the correlation looks really, really weak in this particular example. So let's try to find a linear correlation. Here are some notation that will not be that important for us because we will be using technology to find linear correlation. What we should know is that n is a number of pairs of data, so that's essentially your sample size. Our R is going to be the linear correlation for our sample. This is our statistic. Our rho, again, this is called rho, and that is a linear correlation coefficient for the population. So this is a parameter. Just to remind us, between parameters and statistics, our mean for a population, when we do hypothesis testing, we use mu for a population, and when we do our computations, we use x bar. Our standard deviation values for a population would be sigma, for a sample would be s. Our proportion symbols would be p for the population and p hat for a sample. And so our correlation coefficient is going to be rho and R. So notice how I wrote this rho a little bit different from the P, and that is the Greek letter rho. Here's a complicated formula that fortunately we won't have to memorize or remember. We will be using technology to compute this for us. So let's skip over this page. Now, when we get our correlation coefficient R, we're interested in finding whether this is a good correlation or not so good correlation. So to test or to figure out whether it's good or not good, we're going to use table A5. That is the Pearson table for correlation. Remember that when we're dealing with correlation here, we're looking at linear correlation. So if you get a very bad correlation, a correlation that's close to 0, you can say that there's no linear correlation, but there still might be some non-linear type of relationship. Here are some of the properties for our linear correlation coefficient. Our linear correlation coefficient R should always be between -1 and 1. We have another property that says if you convert one of the variable scales from one scale to another, for example, if you're going to change your x value from centimeters to inches, then your R correlation coefficient does not change. So imagine all those numbers changing according to a change in units, that you're still going to have the same correlation coefficient R. Correlation coefficient is not affected if you change your x and your y values. The correlation coefficient measures the linear relationship, and correlation coefficient is fairly sensitive to outliers. Just to get a feel for the correlation coefficient, here is a small set of values that takes a look at shoe print, size in centimeters, and the height, size in centimeters. We can start by looking at a scatter plot where the shoe print is the x variable and the height is the y variable. And here are the 5 sets of data, or 5 sets of points. And although the points don't all fall in a straight line, we can kind of approximate this data set with a line. And the line is increasing, so we can say that it has a positive correlation. And let's actually check that correlation. Well, we don't know if it has correlation yet, but we'll check to see if there is correlation. Using technology like Minitab or StatDisk or our calculator, we see that the correlation coefficient is 0.591. And we'll talk about how to get this when we actually do an example from the beginning. Based on this value that you get, 0.591, you want to compare that with the critical value that we're going to find from table A5. So in table A5, we remember that we have 5 pairs of data, and let's assume that we're going to use our alpha of 0.05. Then we see that our critical value is going to be given by this number, 0.878. So on a number line between -1 and 1, if we mark our critical values at positive 0.878 and negative 0.878, those can be our markers to determine whether we have correlation. So anything from 0.878 going to positive 1 will have correlation. Anything going from 0.878 negative going to -1 will also have correlation. But anything in between those two critical points will have no correlation. So we see that our sample data produced a correlation coefficient of 0.591, and that is not close to 1 or -1. So we can say that there is no correlation. The R squared also plays an important value, an important part. It turns out that the value of R squared is the proportion or the percentage of variation in Y, the Y variable that's explained by our linear regression line, our linear relationship. In our example, the R was 0.591. If you square that, you get 0.349. And so we can say that about 34.9% of the variation in height can be explained by the linear relationship between the x and the y variables. We want to watch out for some common errors that are involved when we're doing linear correlation. There's a famous line that says correlation does not imply causation, and so what that means is that if you find correlation, it doesn't mean that the x variable causes the y variable to happen. The averages may suppress variation or individual variation and make your correlation coefficient unnaturally large. So if you're taking a bunch of averages instead of using the raw values, you may not get an accurate account for your correlation. And linearity, another common mistake, turns out that there might be some relationship that's not linear, and so you don't want to dismiss that. If you get a really bad correlation, a linear correlation, you should check your data, or at least your scatter plot, to see if there's some other form. And here is the correlation does not imply causation phrase again as another caution. Let's go to part 2, where we're going to actually do a formal hypothesis test. So in a formal hypothesis test, we want to test whether there's a significant linear correlation between two variables, our x and y variable. So for this, we're going to want just a handful of notations: n, r, and rho. N is the number of pairs of data sets that we have. R is the linear correlation for our sample. And rho, which we're not going to know, but we're going to make assumptions about, is going to be the linear correlation for our population. So this is our parameter. So the requirements for our hypothesis test: we want our data to be simple and random, much like the hypothesis test that we've had in chapters 8 and 9. We want a visual examination of the scatter plot that looks like it could be a straight line pattern. And we want to acknowledge to see if there are any outliers, and we may have to remove them. So for a hypothesis test, we do have the null and alternative hypothesis, and it's going to be the same for every single hypothesis test that you do in this chapter. So just remember to write these two things down. Our h naught is rho is equal to 0, and our h1 is rho is not equal to 0. The null hypothesis says that there is no correlation, and the alternative hypothesis is our claim that assumes that there is linear correlation. We're going to be interested in finding a couple of things. We're going to want to find our R value, and then we're also going to want to find our P value. When we check for our R, we're going to take a look at R as being close to 1 or negative 1. So we're going to establish our critical values here. I'll call it CV for critical value. One's positive, one's negative. And so if the CV is bigger than, if R is bigger than the CV in the positive side, that's easy to acknowledge. It's just going to be the one that's the values that are closer to 1. But on the negative side, we have to look at it the other way. It's going to be these values that are closer to -1. And so when that happens, you reject the null hypothesis and you conclude that there is, in fact, a linear correlation. On the other side over here, we're looking at if the critical value is, if R is less than the critical value in absolute value. So the CVs and CVs, we're talking about R that's between the two critical values, positive and negative. So if that happens, then we fail to reject the null hypothesis and we conclude that there is not a sufficient evidence to support linear correlation. Here is an example that we can work with. Again, it's the paired shoe print and height from 5 males that we were talking about. And so let's do a formal hypothesis test. Our formal hypothesis test begins with the null and alternative hypothesis. And we did this work already, and we saw that there was a correlation coefficient of 0.591. And with a correlation coefficient of 0.591, we found that our critical value was 0.878, and we saw that this, the test statistic was not bigger than the absolute value of the critical values, and so we concluded that there was no correlation for this. And so there's no correlation. We failed to reject the null hypothesis and conclude that there is not sufficient evidence to support the claim of linear correlation. So we can simply say that there's no correlation. Another method to approach this is to use what's called the traditional method, using the t-test, and for this you would need to find a t-value. Now, the difficult part about that is that you need to compare this with a critical t-value. This time your degrees of freedom is n-2 compared to n-1 from the last chapter. And we're going to look at table A3. Now, I would suggest not to do this. This is not recommended. Because the other values are a little bit easier to deal with. The easiest way to deal with a hypothesis test is with a p-value, and with our technology we can find our p-values. The p-value for this particular problem looks like it's going to be 0.294, and if we look at that as our p-value, we simply compare our p-value with the significance level, and since 294 is bigger than 0.5, we fail to reject the null hypothesis. And so we come to the same conclusion where we don't support the claim of linear correlation. This problem says that the data shown below is of the selling price and the list price of homes sold in 100,000s. Construct a scatter plot, find the value of the linear correlation coefficient R and the p-value, and then use a 0.05 significance level to see if there is evidence of linear correlation between the two variables. Alright, we're going to go straight to our calculator for this. Well, actually, we're not going to go straight to our calculator. We want to first identify our null and our null and alternative hypothesis. Since this is a a hypothesis test, we need to start off with these two pieces of information. And both of these are a row variable, and the first one is row is equal to 0. That's our null hypothesis, always our null hypothesis, and our alternative hypothesis is not equal to 0. And we can think of this as the statement that says there's no correlation for the null hypothesis, and then there is correlation for the alternative hypothesis. And we can also think about this as a claim. Alright, now to our calculators. The first thing we need to do is we need to go to Stat and Edit and make sure that we have correctly and properly inputted our lists in L1 and L2. So we got 403, 300, 380. Those are like the first three numbers on my L1 column, and everything else is inputted correctly. And then L2 column is 412, 315, and 389, etc. So once we do that, if we want to see the scatter plot of it, we go to second function and stat plot. And what we want to do is we want to make sure that plots 2 and 3 are turned off. If it's not, just hit 4 and enter and then go back to this screen. If it is like this, in this case, we want to go to plot 1. Let's turn this on. If it's not already on, just click on enter while you're blinking on the on button. And then down 1, the type of plot we want is a scatter plot. So that's already chosen. We'll go down again. Our X list is in L1, our Y list is in L2. And the mark that we will use is a square that makes a nice big mark for the dots. Okay, let's go second function and quit to go back to our main screen, and let's hit zoom. And then you can scroll down and look for it, but I think in most calculators it's the number 9, the zoom stat. So that's what we want to select. We can press enter since I already have this highlighted, or if you didn't feel like scrolling down, you could have just hit 9 and that would have given you the zoom plot. So here is our scatter plot. Now what we want is we want to find our correlation coefficient and our p-value. So we can do that in our lin-reg t-test. Let's go to stat, test, and instead of scrolling down, I'm going to scroll up since I know it's pretty close to the bottom and this kind of loops around. So I'm going to look for lin-reg t-test here. I'll hit enter, and my X and Y list are in L1 and L2. Our frequency is always going to be 1. We don't need to change that. And we'll select, according to our alternative hypothesis, we will select the not equal to button. Now the reg EQ, it's good to be able to store this into Y1, and you only have to do this once, and all the other future lin-reg t-tests, this Y1 will automatically be here. So if you don't have this Y1 here, let's say it's blank like it is right now, you go to vars, yvars, and function, so that's the number 1, or hit enter, and there's Y1. So this will store your regression equation into Y1, and that's going to be covered in our next section. Let's go to calculate and hit enter. And here is half of the values that we want. The p is our p-value. So let's take that. If you scroll down a little bit more here, you'll see the other pieces of information that will be important for us. Okay. We are asked to identify our R value, our correlation coefficient. the R value is all the way at the bottom. That's 0.992. And our p-value is near the top, and that is 1.4. Now there's an e to the -7 here, which is to say that our p-value is actually 0.3456614, which is really close to 0. And so I would use 0 plus to represent a number that's really, really close to 0. Alright, so we have these two values picked out, and so now we can choose one or the other to make our conclusion. Let's say we're using this R, 0.992, and just by looking at it, it looks really close to +1, and that would make sense with a positive correlation here. So I would think that this is going to conclude in a positive correlation. What we do want to know is our critical values, CV, and we have a positive part and a negative part to this. So we'll find that using our table. Let's see if I can pick out our table. We have 3, 4, 5, 6, 7, 8, 9. We have 9 numbers over here. So we're looking at 9, and then we're assuming at a 0.05 significance level. So we're looking at 0.666, negative 0.666 on the left side, positive 0.666 on the right side. And more importantly, our correlation coefficient is in the correlated section, close to +1 in this case. So we can say that there is positive correlation. So that's our conclusion here, and we should get the exact same conclusion if you're looking at the p-value. So let's look at the p-value. We note that the p-value is less than the significance level. That is, this really, really small number is less than 0.05. So we reject our null hypothesis. And when we reject our null hypothesis, we're rejecting the null correlation. So again, we're going to end up with the same conclusion. So what is our conclusion? Based on the data, it looks like we can conclude that there is, now it's always good to just say positive or negative depending on what the sign is for your correlation coefficient. So in this case it's positive. So we can conclude that there is positive linear correlation, and we want to include what the variables are. So the linear correlation is between our list price and our selling price. For homes that were sold. Okay, so that's our conclusion, and the main part of our conclusion is that we say that there is a positive linear correlation. So that is going to be it for our hypothesis test. So hope that works, and we're looking at streamlining our 8-step process to just basically 3 steps here. We have the hypothesis build up, and we have either the R values or the P values, and then we make our conclusion based on those values that we saw. Okay, I hope that helps.